There is a strange tension in the universe, a quiet contradiction that hides in plain sight. We map the cosmos as if it is complete, measurable, knowable. And yet, the closer we look, the more we realize that a vast part of it is slipping away from us. Not because it is far, but because of something far more unsettling. The universe does not show us itself. It shows us only a version of itself, a fading memory stretched across time. And here is the part that scientists rarely phrase aloud. The edge of the universe is not out there somewhere. It is wrapped tightly around us, and it is moving. Not a wall, not a barrier, but a horizon, the limit of what reality allows us to witness from this single point in space and time. A boundary shaped not by matter, but by time itself, by the age of the cosmos, and the relentless expansion that has been pulling galaxies away faster than their own light can reach us. This boundary behaves like a paradox. Move a billion light years in any direction, and the universe redraws the map, creating a new edge, with new galaxies inside and others erased forever. An observer in a distant cluster would see a universe with different limits, different histories, different horizons. The cosmos does not have one boundary. It has trillions, each one centered on a different observer, each quietly insisting that reality is relative to where you stand. This idea sounds philosophical, almost abstract, until you realize it is not speculation. It is the mathematics of general relativity, the same equations that describe black holes and the bending of starlight. And those equations reveal something deeply counterintuitive. Distance is not a fixed quantity. It stretches. It evolves. It depends on when you measure it. Light exposes this illusion most clearly. A star 10 light years away offers us its decade-old reflection. A galaxy 10 billion light years away becomes a message from a universe that no longer exists in that form. A universe denser, hotter, more chaotic than anything around us now. And while that ancient light has been traveling toward us, space itself has been expanding underneath it, carrying the galaxy farther and farther away, so that the distance we quote today is not a distance that light ever traveled. And this is where the first quiet contradiction appears, the kind that keeps cosmologists awake at night. Some galaxies are receding from us faster than the speed of light, not because they are breaking physics, but because the space between us and them is growing at a rate that outpaces the photons trying to cross it. Light emitted long ago can still reach us, but light emitted now will never arrive. Those galaxies are drifting beyond the horizon, disappearing from the observable universe in real time, not with a bang, but silently, as expansion tugs them away until they vanish from the story of everything we can ever measure or know. And yet, here is the strangest part. We speak of the edge as if it is the end of the universe, when in truth, it is merely the end of our memory of it. The edge of the observable universe marks this limit, the boundary beyond which light has not had time to reach us since the Big Bang. And its location depends on the expansion history, on the changing balance between matter, radiation, and dark energy over cosmic time. In the early universe, when matter and radiation dominated, the edge grew steadily as light from more distant regions finally arrived. But now, with dark energy driving an accelerating expansion, the edge is approaching a maximum size, a limit beyond which it cannot grow, because distant galaxies are receding too fast for their light to ever catch up. Yet the deeper you look, the stranger the picture becomes, because this edge is not permanent, not a fixed feature of the cosmos, but a moving boundary that shifts as the universe ages, revealing some regions while hiding others. And the universe that future observers will see will be dramatically different from the universe we observe today. Smaller in some sense, darker, more isolated, with most of the cosmic web carried beyond the horizon and the evidence for expansion, for the Big Bang, for the deep history of the cosmos, gradually fading into invisibility. This creates a kind of temporal selection effect, where the observability of the universe depends on when you are observing. And we happen to live in an era when the cosmos is old enough to have formed stars and galaxies and complex structures, but still young enough that the distant galaxies, the cosmic microwave background, the large-scale structure of the universe remain visible and accessible to study. But here is the detail scientists rarely discuss. Billions of years from now, observers in our galaxy or in whatever structure remains after the Milky Way merges with Andromeda will look out at a night sky containing only a handful of nearby galaxies, gravitationally bound and held together against the expansion, while all the distant clusters, all the rich tapestry of the cosmic web, all the evidence that once allowed us to discover the expansion of the universe will have been carried beyond the cosmic horizon, redshifted into invisibility, lost to observation forever. Those future astronomers might not even realize that the universe is expanding, because the only galaxies they can see will be moving in complex patterns driven by local gravity, rather than the simple recession driven by cosmic expansion. And the truth about the origin and evolution of the universe might be inaccessible to them, hidden not by a lack of intelligence or technology, but by the fundamental structure of space-time itself. And this raises a question that cuts to the heart of cosmology. What evidence has already disappeared beyond our own horizon? What structures or patterns or features of the early universe have been carried so far away that we cannot observe them? And without observing them, how can we know they existed? How can we test whether our theories accurately describe the universe as a whole or merely describe the limited region we happen to inhabit? The edge of the observable universe is not just a boundary in space. It is a boundary of knowledge, a limit on what can be verified, what can be measured, what can be known with certainty. And beyond that boundary lies not empty space, but unobservable space. Regions of the cosmos that continue to exist, to evolve, to form structures, entirely independent of whether we can see them, entirely beyond the reach of any experiment we could ever perform. And this is the point where our assumptions start to bend, because cosmology, unlike other sciences, cannot put the universe in a laboratory, cannot run controlled experiments, cannot test theories by manipulating the object of study, and instead must rely on observation, on gathering light from distant sources and inferring the properties of the cosmos from that light. And if that light is systematically biased, if the regions we can observe are not representative of the whole, then our theories might be accurate descriptions of our local bubble, but misleading descriptions of the universe at large. There is evidence, tentative but persistent, that this might be the case, that the region of space we inhabit is not perfectly typical, not a fair sample of the cosmic average. The universe, when surveyed at the largest scales, appears smooth and uniform, with galaxies distributed roughly evenly in all directions. But within that overall homogeneity, there are fluctuations, variations in density, regions where galaxies cluster more tightly, and regions where they are sparse. And these variations affect how light travels, how distances are inferred, how we interpret the redshifts and brightnesses of distant objects. If Earth sits within a region that is slightly underdense compared to the cosmic mean, a large void or low-density bubble extending hundreds of millions of light years, then light traveling through that region would be affected differently than light traveling through an average density region, and the effects would accumulate over cosmic distances, creating systematic biases in our measurements that we might not recognize as biases because we have no external reference, no other vantage point from which to compare. Yet none of this fully explains what comes next, because when astronomers measure the expansion rate of the universe using different methods, they obtain results that do not quite agree, values that differ by nearly 10%. And this discrepancy, known as the Hubble tension, has persisted for years, resisting attempts to explain it as a statistical fluke or an instrumental error. Measurements made using nearby supernovae, calibrated against Cepheid variable stars, give an expansion rate around 73 kilometers per second per megaparsec, while measurements derived from the cosmic microwave background, using the physics of the early universe, give a value around 67. The difference is small but statistically significant, and it suggests that either our understanding of the physics is incomplete, missing some component or process that affects the expansion, or our observations are systematically biased in ways we do not fully understand, perhaps because we live in a region where the local expansion rate differs from the global average, where the density structure or the flow of matter creates conditions that are not representative of the universe as a whole. But this is where the universe begins to behave unexpectedly, because if the expansion rate varies from place to place, if there are regions where space expands faster or slower than the cosmic mean, then many of the assumptions that underlie modern cosmology start to unravel. The standard model assumes homogeneity, the idea that the universe is smooth and uniform when averaged over sufficiently large scales, and this assumption is necessary for building tractable mathematical models, for making predictions, for interpreting observations. But it is also an idealization, a simplification that might break down when examined closely enough. The cosmic microwave background, that faint glow of radiation from the early universe, is remarkably uniform, varying in temperature by only about 1 part in 100,000. And this uniformity is one of the strongest pieces of evidence for the Big Bang. But uniformity at one moment in time does not guarantee uniformity at all moments, does not prove that the smoothness we observe extends beyond the regions that were causally connected in the early universe, that underwent inflation together, that were homogenized by physical processes operating within a limited domain, and quietly. Another contradiction appears in the data, because the cosmic microwave background, when analyzed with exquisite precision by satellites like Planck, reveals patterns that are harder to explain, subtle alignments and correlations that suggest the presence of large-scale features extending across the entire sky. There is an unexpected alignment in the largest scale temperature fluctuations, a tendency for certain modes to point in a particular direction, as if the universe has a preferred axis, and this has been called the axis of evil. though the name is more playful than sinister, and most cosmologists suspect it is a statistical artifact, a product of noise or foreground contamination, or simply the result of seeing patterns in limited data. But there is also a hemispherical power asymmetry, a tendency for one half of the sky to have slightly stronger fluctuations than the other, and a cold spot, a region significantly colder than expected, that has resisted explanation for years. And while each of these anomalies can be dismissed individually, taken together, they form a pattern that is more difficult to explain away, and they raise the possibility that the universe is not perfectly isotropic, not the same in all directions, and that there are large-scale asymmetries or structures that we do not yet understand. Yet the deeper you look, the stranger the picture becomes, because there are structures in the observable universe that challenge the assumptions of homogeneity in more direct ways. Concentrations of galaxies and clusters so large that they seem to violate the limits of what should be possible, given the age of the cosmos and the time available for gravitational collapse. The giant arc, a structure spanning roughly 3 billion light-years, is one such example, discovered in surveys of galaxy positions and difficult to reconcile with the standard model, because structures this large should not have had time to form, should not exist if the universe is as smooth and uniform as we assume. Similarly, the huge large quasar group, a collection of quasars spread across an enormous region, pushes the boundaries of what current theories predict. And there are other examples, other large-scale structures that seem too big, too massive, too coherent to have assembled in the time available. And while these structures do not overturn the Big Bang model, they introduce tensions, places where observation and theory do not quite mesh, where the data suggests more complexity, more structure, more variation than the simplest models allow. And this is the point where our assumptions start to bend. Because if structures this large exist within the observable universe, within our cosmic horizon, then it is natural to ask whether even larger structures exist beyond the edge. Structures so vast that we can see only a fragment, a small piece that appears as an anomaly or an alignment in the patterns we observe. The edge of the universe might not just be a limit of visibility, but also a source of distortion, cutting through structures that extend beyond our reach, showing us partial views that are misleading or unrepresentative of the whole. And the smoothness we observe might be an artifact of the limited scales we can probe, a local property that does not extend to the universe at large. But here is the detail scientists rarely discuss: the cosmic web, that vast network of filaments and voids that spans the observable universe, connecting clusters of galaxies along thread-like structures separated by enormous empty regions, extends all the way to the edge of our observational reach. And there is no reason to believe it stops there. No indication that the filaments we see near the horizon terminate at some boundary, rather than continuing outward, connecting to galaxies and structures that lie beyond the limit of what we can observe. This continuity suggests that the edge is arbitrary, a consequence of our limited perspective, rather than a real feature of the cosmos, and that the universe beyond the horizon is likely similar to the universe within it, at least in its large-scale properties. But we cannot test this assumption, cannot verify that the laws of physics apply uniformly across regions we cannot observe. And this introduces a fundamental uncertainty into cosmology, because the edge divides the cosmos into the testable and the untestable. The regions where theories can be checked against observation, and the regions where theories must be accepted on faith or abandoned as unprovable. And in these mismatches, a different story begins to form. A recognition that the universe we observe might be only one perspective among countless others, one view shaped by our particular location and moment in cosmic time, and that other observers in other galaxies, other regions, other epochs would see different observable universes, overlapping with ours but not identical, revealing different galaxies, different structures, different features of the cosmic web. This multiplicity of perspectives is not a philosophical abstraction. It is a direct consequence of the geometry of space-time, of the way light travels through an expanding universe, of the fact that information propagates at a finite speed and cannot reach us from regions whose light has not had time to arrive, or whose recession velocity exceeds the speed of light. The edge we observe is our edge, not the universe's edge, and every other observer in the cosmos would define their own edge, their own boundary, their own sphere of observability, and there would be no single, objective edge that all observers would agree upon. No universal boundary that divides the cosmos into the observable and the unobservable. Yet none of this fully explains what comes next, because the edge is not only a spatial boundary, but also a temporal one, a limit on how far back in time we can see. And that limit is determined not just by the age of the universe, but by the physics of light propagation, by the transition from opacity to transparency that occurred when the universe cooled enough for neutral atoms to form. Before that moment, roughly 380,000 years after the Big Bang, the universe was filled with a hot, dense plasma, a sea of ionized hydrogen and helium that scattered photons in every direction, making space opaque to electromagnetic radiation. When neutral atoms formed, when electrons and protons combined, and photons were suddenly free to travel without being scattered, the universe became transparent, and the light from that moment has been traveling ever since, stretched by expansion into the microwave part of the spectrum, forming the cosmic microwave background that surrounds us like the inner surface of a sphere. This glow represents the furthest back in time we can see using light, the edge of the observable universe in the temporal direction. And beyond it lies the opaque era, the time when the universe was filled with plasma and light could not propagate freely. And to probe that era, we would need to use other signals, other messengers such as gravitational waves or neutrinos, which can travel through plasma without being scattered and might carry information from epochs even closer to the beginning. But this is where the universe begins to behave unexpectedly, because the cosmic microwave background, though remarkably uniform, is not perfectly smooth, and the tiny temperature fluctuations it contains, variations of about 1 part in 100,000, are the seeds of all structure in the universe. The density variations that grew through gravitational collapse over billions of years to form galaxies, clusters, voids, and the entire cosmic web. By analyzing these fluctuations, by studying how they vary across different angular scales, cosmologists can extract an enormous amount of information about the early universe, about the density of matter, the presence of dark energy, the curvature of space, the speed of sound in the primordial plasma. And these measurements have allowed us to determine the age, composition, and geometry of the cosmos with remarkable precision. Yet the deeper you look, the stranger the picture becomes. Because the largest scale fluctuations in the cosmic microwave background, those that span the entire sky, are determined by processes that operated on scales comparable to or larger than the observable universe itself. And if those processes involved regions beyond our current horizon, then the patterns we see might carry faint imprints of something larger, something we cannot observe directly, but that influence the region we can see. This is one of the ways cosmologists attempt to probe beyond the edge, to use the patterns within the observable universe to infer properties of the unobservable. And it is a subtle, difficult, highly model-dependent endeavor, because the same observable patterns can sometimes be explained by different underlying models, different assumptions about initial conditions, about the physics of inflation, about what lies beyond the horizon. The cosmic microwave background is full of such ambiguities, places where multiple interpretations are consistent with the data, and disentangling them requires additional observations, independent lines of evidence, careful statistical analysis that accounts for all possible sources of uncertainty and bias. And this is the point where our assumptions start to bend, because the process of interpreting the cosmic microwave background requires us to assume a cosmological model, to assume values for the expansion rate, the density of matter, the properties of dark energy. And if those assumptions are wrong, if our model does not accurately describe the universe, then the parameters we infer from the cosmic microwave background will be systematically biased, and the picture we build of the early universe will be distorted in ways that are difficult to detect. Yet none of this fully explains what comes next, because in recent years, observations from the James Webb Space Telescope have revealed galaxies in the early universe that appear more massive, more evolved, more structured than models predicted. Galaxies forming when the cosmos was only a few 100 million years old, with stellar populations that seem too mature, too chemically enriched, too organized into spiral or disk structures given the time available for growth and assembly. These discoveries have sparked intense debate because they suggest that galaxy formation in the early universe was faster, more efficient, more complex than current theories allow, and this might indicate that something is missing from the models, some process that accelerates star formation or gas collapse, or it might suggest that the observations are being misinterpreted, that the redshifts are uncertain, that the masses are overestimated, that the galaxies are not as old or as evolved as they appear. But here is the detail scientists rarely discuss. If these galaxies are real, if their properties are accurately measured, then they challenge not just the details of galaxy formation, but the broader assumptions about how structure grows in an expanding universe, about how quickly dark matter halos can collapse, about how efficiently gas can cool and condense into stars. And resolving these tensions might require revisions to the standard cosmological model, or might point toward new physics, new processes, new phenomena that operate in the early universe but are not captured by current simulations. And quietly, another contradiction appears in the data, because the James Webb Space Telescope has also discovered supermassive black holes in the early universe. Black holes with masses millions or billions of times the mass of the Sun, existing when the universe was less than 1 billion years old. And the formation of such massive objects in such a short time is difficult to explain within the standard picture of black hole growth. Black holes are thought to form from the collapse of massive stars or from the direct collapse of gas clouds, and they grow by accreting matter from their surroundings. But accretion is limited by radiation pressure, by the fact that infalling matter heats up and emits light that pushes against further infall, and this sets a maximum rate at which black holes can grow, known as the Eddington limit. To reach millions or billions of solar masses in less than a billion years requires either that black holes formed with large initial masses, much larger than the masses of individual stars, or that they grew faster than the Eddington limit allows, perhaps through super-Eddington accretion, through mergers with other black holes, or through some other process that is not well understood. Yet the deeper you look, the stranger the picture becomes, because these early galaxies and supermassive black holes are not isolated anomalies, but part of a broader pattern, a growing body of evidence that the early universe was more dynamic, more active, more richly structured than the simplest models suggest. The cosmic web was assembling itself from the primordial density fluctuations. Galaxies were colliding and merging. Gas was flowing along filaments into dense nodes, where stars ignited in vast bursts of activity. And the conditions in those early epochs might have been different enough, extreme enough, that the processes governing star formation and black hole growth operated in ways that are not well captured by models calibrated on the present-day universe. And this is the point where our assumptions start to bend, because the observations we make of the early universe are necessarily indirect, filtered through billions of years of cosmic expansion, affected by gravitational lensing, by redshift, by dimming, by all the accumulated distortions that light suffers as it travels across vast distances, and reconstructing the true properties of those early galaxies from the altered light we receive requires models, assumptions, careful calibration against standards that might themselves be uncertain. But here is the detail scientists rarely discuss: the standards we use to measure cosmic distances, the relationships between brightness and distance, between redshift and recession velocity, between angular size and physical size, are all derived from observations of relatively nearby objects, galaxies within a few billion light years, and extrapolating those relationships to much greater distances, to the edge of the observable universe, requires assuming that the universe is homogeneous, that the properties of space and the behavior of light are the same everywhere. And if that assumption is wrong, if there are variations in density or expansion rate, or the properties of dark energy from place to place, then the distances we infer for the most remote objects might be systematically incorrect, and the properties we calculate for those objects, their masses, their ages, their luminosities, might be biased in ways that are difficult to detect or correct. And in these mismatches, a different story begins to form, because the edge of the observable universe is not just a boundary of visibility, but also a source of uncertainty, a region where our measurements become least reliable, where the signal is faintest, where the noise is strongest, where the assumptions we make have the largest impact on the conclusions we draw. The galaxies we observe near the edge are seen as they were when the universe was young, when conditions were different, when the physics might have operated in unfamiliar regimes. And interpreting those observations requires extrapolating our models backward in time, across billions of years of cosmic evolution, And every extrapolation introduces uncertainty. Every assumption adds potential for bias, and the edge becomes not just a limit of observation, but a frontier, where certainty gives way to inference, where measurement gives way to interpretation, where science brushes against the limits of what can be known. Yet none of this fully explains what comes next, because the edge of the observable universe is not a single, well-defined boundary, but a collection of different horizons corresponding to different physical processes, different definitions of distance, different limits of observation. There is the particle horizon, the boundary beyond which light has not had time to reach us since the Big Bang. And this is what we usually mean when we speak of the observable universe. There is the event horizon, the boundary beyond which light emitted now will never reach us, due to the accelerating expansion driven by dark energy. And this horizon is smaller, closer, marking the limit of what we can ever observe, even in principle, even if we wait forever. There is the Hubble horizon, the distance at which the recession velocity of galaxies equals the speed of light. And beyond this horizon, objects are receding faster than light, though we can still observe them if their light was emitted long ago when they were closer. Each of these horizons marks a different kind of edge, a different limit, and they do not all coincide, do not all occupy the same location in space or the same moment in time. But this is only the beginning of the confusion, because once you think you understand these horizons, the universe quietly shifts the ground beneath your feet. There is a moment, subtle but decisive, when our understanding of the universe begins to slip. Not because the cosmos hides its rules, but because those rules shift depending on how far and how deep we dare to look. The horizon we see today is not the same horizon that existed 1 billion years ago. It is not the same horizon another observer will see 1 billion years from now. And this simple fact carries a quiet shock. The universe does not reveal one boundary, but a boundary that moves. It breathes, expands, withdraws, reshapes itself with every epoch, as if reality were a story told in slow motion, always rewriting its own edges. And here comes the part cosmology rarely says aloud. If our measurements of expansion, our distances, our redshifts, our estimates of matter and radiation are even slightly biased, even subtly skewed by what we cannot see, then the edge we calculate is not the true one. It becomes a reflection of our assumptions, not the universe itself. A map drawn from inside a fog. But the intrigue deepens when we introduce dark energy, the quiet architect behind cosmic acceleration. 70% of the universe, yet almost nothing is known about it. Not its origin, not its mechanism, not even whether it is truly constant. The only thing we know for certain is that it pushes space apart faster and faster, so fast that galaxies do not merely drift away from us, but are carried beyond reach, beyond visibility, beyond interaction. If the universe has an edge, dark energy is the hand that moves it. And here's where theory bends into something stranger. Every attempt to measure this hidden force requires staring at the faintest signals the cosmos offers. Distant supernova, flickering on the edge of detection. Galaxies so far away, their light arrives stretched into ghost-like whispers. Distortions of space-time so slight, they resemble optical illusions. The measurements lie at the limits of our tools, at the limits of confidence, at the limits of what physics can currently decode. And the more we push toward that boundary, the more the uncertainty grows, like trying to sketch a coastline while standing in deepening fog. This means something profound and unsettling. Our understanding of the universe's edge depends on forces we do not yet understand, measured with tools almost too weak for the task. A cosmic boundary determined by a mystery, and quietly, another contradiction appears in the data. Because measurements of dark energy's properties using different techniques do not always agree, do not always yield consistent results. And this might indicate that our understanding of dark energy is incomplete, that there are effects or processes we have not accounted for. Or it might suggest that the observations themselves are affected by systematic biases, by foreground contamination, by selection effects, by all the subtle ways that real data deviates from the idealized assumptions of theoretical models. But here is the detail scientists rarely discuss. The equation of state of dark energy, the relationship between its pressure and its density, is constrained by observations to be very close to -1, the value expected for a true cosmological constant. But the uncertainties are large enough that small deviations cannot be ruled out. And if dark energy is not exactly constant if it evolves over time, then the expansion history of the universe will differ from what we currently assume. And the location of the cosmic horizon, the size of the observable universe, the fate of distant galaxies, all of these will change in ways that depend on the details of how dark energy behaves. Yet none of this fully explains what comes next, because understanding the edge of the universe requires not just understanding dark energy, but also understanding the geometry of space itself, the curvature of space-time, the topology of the cosmos. And these are among the most fundamental questions in cosmology. Questions about the shape and size and connectivity of the universe at the largest scales. General relativity tells us that space can be flat, like an infinite Euclidean plane, or positively curved, like the surface of a sphere, or negatively curved, like a saddle. And the curvature is determined by the total energy density of the universe, by the sum of matter, radiation, and dark energy. And if the density equals a critical value, then space is flat. And if it exceeds that value, space is positively curved. And if it falls short, space is negatively curved. Observations of the cosmic microwave background suggest that the universe is very nearly flat, so close to the critical density that any curvature is too small to measure. And this flatness is itself a puzzle, an indication that something acted to smooth and flatten space in the early universe, and that something is thought to be inflation. And this is the point where our assumptions start to bend, because inflation, that brief period of exponential expansion in the first fraction of a second after the Big Bang, is invoked to explain not just the flatness of space, but also the uniformity of the cosmic microwave background, the absence of certain exotic relics from the very early universe, the origin of the primordial density fluctuations that seeded the formation of structure. And it is a remarkably successful theory, consistent with a wide range of observations. But it is also incomplete, because we do not know what caused inflation, what field or particle drove the exponential expansion, why inflation started when it did, why it ended, what happened before inflation, whether inflation is a one-time event or an eternal process that continues in other regions beyond our horizon. The edge of the observable universe might mark not just the limit of our visibility, but also the boundary of the inflated patch, the region of space that underwent inflation together and became causally connected. And beyond that boundary, there might be other patches, other domains, each with its own history, its own properties, its own laws of physics, forming a multiverse of staggering scale and complexity. Yet the deeper you look, the stranger the picture becomes, because this multiverse, if it exists, would be forever beyond our observational reach, causally disconnected from us by the structure of space-time, and the only evidence for its existence would be indirect, subtle imprints on the cosmic microwave background, or the distribution of galaxies, hints of collisions between bubbles or gravitational influences from regions beyond our horizon. And detecting such signals is extraordinarily difficult, perhaps impossible. And even if signals are detected, interpreting them is fraught with ambiguity, because the same patterns might be explained by other causes, other processes operating within our observable universe. The edge of the universe, in this picture, becomes not a boundary between space and non-space, but a boundary between the knowable and the unknowable, between the regions where science can make testable predictions and the regions where science gives way to speculation, to inference, to models that are elegant and compelling, but cannot be verified through observation. And in these mismatches, a different story begins to form, a recognition that the edge is not just a physical boundary, but an epistemological one, a limit on what can be known, what can be measured, what can be tested. Through the methods of empirical science, cosmology, more than any other science, confronts this limit, because the object of study is the universe as a whole, and the universe cannot be manipulated, cannot be experimented on, cannot be viewed from the outside, and the only data we have is the light that reaches us from distant sources, light that has been traveling for billions of years, light that carries information about the state of the universe at various moments in its history, but does not reveal the present state, does not show us what those distant galaxies look like now, at this moment, because the concept of now is ambiguous in general relativity, dependent on a choice of reference frame, and there is no unique way to slice space-time into moments of simultaneous time that all observers would agree upon. But here is the detail scientists rarely discuss. The edge of the observable universe is not where the universe ends, but where our information ends, where the signals we can receive, the measurements we can make, the observations we can perform reach their limit. And beyond that limit, the universe continues. Galaxies form and evolve. Stars ignite and die. Black holes merge. Structure grows. And all of this happens entirely independent of whether we can observe it, entirely beyond the capacity of any telescope or instrument or theory to access. The edge divides the cosmos into the observed and the unobserved, the regions we can study and the regions we can only imagine. And this division is not a temporary limitation that will be overcome with better technology, but a fundamental feature of space-time, a consequence of the finite age of the universe and the finite speed of light. And it means that cosmology is inherently incomplete, that there will always be questions about the universe as a whole that cannot be answered definitively, regions whose properties cannot be measured, assumptions that cannot be tested, and we must learn to live with this incompleteness, to work within these constraints, to make the best possible inferences from limited data while acknowledging the boundaries of what can be known. Yet none of this fully explains what comes next, because even within the observable universe, Even within the regions we can, in principle, observe, there are limits to what we can actually detect. Limits set not by the speed of light or the age of the cosmos, but by the brightness of objects, the sensitivity of instruments, the presence of foreground contamination, and all the practical challenges that arise when trying to observe the faintest, most distant, most ancient light. The edge of practical observability falls well short of the theoretical edge, and there is a vast region of space whose light has reached us, but whose faint signals are lost in the noise, undetectable with current technology. And closing this gap requires building larger telescopes, more sensitive detectors, more sophisticated methods for processing data and extracting signals from backgrounds. And even with these advances, there will always be a gap, always objects too faint to see, always regions too obscured by dust or too contaminated by foreground sources to study reliably. And this is the point where our assumptions start to bend, because the galaxies we can observe are not a random sample of all galaxies, but a biased sample, weighted toward the brightest, the most massive, the most actively star-forming. And this selection effect means that our picture of the universe is incomplete, skewed toward the exceptional rather than the typical. And extrapolating from this biased sample to draw conclusions about the universe as a whole requires statistical modeling, careful corrections for incompleteness, assumptions about the distributions of galaxy properties that might themselves be wrong if the sample is too biased or too limited. The edge of what we can observe is not the edge of what exists, but merely the edge of what is detectable. And beyond that edge, there are countless faint galaxies, dim stars, diffuse structures that remain invisible, contributing to the total mass and energy of the universe, but leaving no direct imprint on our observations. And accounting for these unseen components is one of the ongoing challenges in cosmology, a source of uncertainty that affects estimates of the total matter density, the rate of star formation, the abundance of dark matter, and many other fundamental properties. But this is where the universe begins to behave unexpectedly, because dark matter, that invisible component that makes up roughly 85% of the total matter in the universe, is itself detected only indirectly through its gravitational effects on visible matter, on the rotation of galaxies, on the motion of galaxy clusters, on the bending of light through gravitational lensing. And we have never observed a dark matter particle directly, never detected it in a laboratory, never measured its properties except through its influence on the things we can see. The edge of the observable universe is filled with dark matter, vast halos surrounding galaxies, filaments connecting clusters, structures that are invisible but shape the cosmic web. And our maps of the universe are really maps of luminous matter, of stars and gas that emit light. And the dark matter distribution can only be inferred from the way that light is affected, from gravitational lensing distortions, from velocity measurements, from subtle correlations between the positions of galaxies. And all of these inferences depend on assumptions about the nature of dark matter, about how it clusters, how it interacts, how it responds to gravity. Yet the deeper you look, the stranger the picture becomes, because there are anomalies in the behavior of dark matter at small scales, discrepancies between the predictions of simulations and the observations of dwarf galaxies, of the inner regions of galaxy halos, of the distribution of satellites around the Milky Way. And these discrepancies might indicate that our understanding of dark matter is incomplete, that the simplest models, which assume dark matter is cold and collisionless, are missing some important physics, some interaction or property that affects how dark matter behaves in dense environments. Or they might indicate that the observations are more complex than they appear, that baryonic physics, the behavior of ordinary matter, gas, and stars, affects the distribution of dark matter in ways that are difficult to model. That feedback from star formation and supernova and black hole activity can redistribute matter and alter the shapes of halos. And disentangling these effects from the underlying properties of dark matter is a subtle and ongoing challenge. And quietly, another contradiction appears in the data, because the abundance of the smallest dark matter structures, the subhalos that should be present in vast numbers according to simulations, does not seem to match what is observed. And this is known as the missing satellites problem. The fact that the Milky Way has far fewer dwarf satellite galaxies than simulations predict. And this might mean that many of the smallest dark matter halos never formed stars, never became visible, remaining dark and undetectable. Or it might mean that the simulations are missing some physics that suppresses the formation of small halos. Or it might mean that dark matter is not quite as cold as we assume, that it has some velocity dispersion, or some interaction that smooths out the smallest structures. But here's the detail scientists rarely discuss. Solving these small-scale anomalies does not require abandoning the dark matter paradigm entirely, does not overturn the overwhelming evidence for dark matter from galaxy rotation curves, from gravitational lensing, from the cosmic microwave background, from the large-scale structure of the universe. But it does suggest that the picture is more complex, more nuanced, more dependent on details we do not yet fully understand. Yet none of this fully explains what comes next, because the cosmic web, that vast network of filaments and voids stretching across the observable universe, is shaped by both dark matter and ordinary matter, by the interplay of gravity pulling matter together and cosmic expansion pulling it apart, by gas cooling and condensing into galaxies, by feedback from stars and black holes, heating and expelling gas, by all the complex processes that govern the formation and evolution of structure over cosmic time. The web extends to the edge of our observational reach. And there is every reason to believe it continues beyond that edge, connecting regions we cannot see, forming patterns at scales larger than the observable universe. And this continuity suggests that the edge is not a boundary of structure, but merely a boundary of visibility, a limit imposed by the finite age of the cosmos and the finite speed of light. And beyond the edge, the universe remains structured, remains dynamic, remains filled with galaxies and clusters and voids, all evolving according to the same physical laws that govern the regions we can observe. And this is the point where our assumptions start to bend. Because if the cosmic web continues beyond the edge, if there are structures at scales larger than the observable universe, then those structures might affect the region. We can see in subtle ways, creating gradients in density or velocity, biasing our measurements, introducing correlations in the cosmic microwave background, or the distribution of galaxies that we might misinterpret as features of the observable universe when they are really imprints of something larger, something beyond our horizon. The possibility that we sit within a large-scale structure, a supervoid, or a supercluster that extends beyond the edge has been suggested as one potential explanation for anomalies in the data, for the hemispherical asymmetry in the cosmic microwave background, for the Hubble tension, for various other discrepancies that resist explanation within the standard model. And testing this possibility is difficult because it requires mapping our position within the cosmic web with extraordinary precision, measuring the density and velocity fields in our local region and comparing them to the cosmic average. And the measurements are subtle, the uncertainties large, the conclusions tentative. But this is where the universe begins to behave unexpectedly, because mapping the cosmic web requires observing galaxies across vast distances, measuring their redshifts to determine their distances. And redshift is not a perfect measure of distance, because it includes not just the cosmological redshift from the expansion of space, but also the Doppler shift from the peculiar velocities of galaxies, the motions driven by local gravitational fields, and disentangling these two components is challenging, especially at large distances where the peculiar velocities are small compared to the cosmological recession, but still significant enough to introduce scatter and bias into distance estimates. The edge of the observable universe is reached by observing the highest redshift galaxies, the most distant quasars, the faintest signals in the cosmic microwave background. And at those distances, the uncertainties in redshift measurements become large. The interpretation becomes model-dependent. The assumptions about the relationship between redshift and distance become critical, and small errors or biases can propagate into large uncertainties in the inferred properties of the universe. Yet the deeper you look, the stranger the picture becomes, because high redshift observations also reveal the universe at early times, when conditions were different, when the density was higher, when structure was just beginning to form. And the galaxies we observe at the edge are not like galaxies today, but represent earlier stages of evolution, building blocks that will merge and grow over cosmic time to form the massive galaxies we see in the nearby universe. By comparing galaxies at different redshifts at different epochs, astronomers can trace the history of galaxy formation, the evolution of star formation rates, the growth of black holes, the assembly of the cosmic web. And this evolutionary picture is one of the great achievements of modern cosmology, a detailed reconstruction of how the universe changed from a nearly smooth, uniform state after the Big Bang to the richly structured cosmos we inhabit today. But here is the detail scientists rarely discuss. This reconstruction depends critically on our ability to date galaxies, to determine their ages from their spectra, from their colors, from their morphologies. And these age estimates are model-dependent, uncertain, subject to degeneracies between age and other properties like dust content or chemical composition. And the evolutionary sequences we infer might be incomplete or incorrect if our models do not fully capture the range of galaxy properties and the processes that govern their evolution. And quietly, another contradiction appears in the data, because some of the highest redshift galaxies, those observed by the James Webb Space Telescope at redshifts above 10, above 11, corresponding to times less than 500 million years after the Big Bang, appear to have properties that are difficult to reconcile with the standard picture of hierarchical structure formation. The idea that galaxies grow through the gradual accretion of gas and the merging of smaller systems. And these galaxies seem too massive, too luminous, too structured for their age, suggesting that the early universe was capable of forming large galaxies more quickly than models predict. This might indicate that the star formation efficiency was higher in the early universe, that gas could cool and collapse more rapidly, that the first stars were more massive and produced more light. Or it might indicate that the mass estimates are uncertain, affected by assumptions about the stellar populations, the dust content, the contribution from active galactic nuclei, and resolving these questions requires more observations, more detailed spectroscopy, more sophisticated modeling that accounts for all the complexities of galaxy formation in extreme environments. Yet none of this fully explains what comes next, because the edge of the observable universe is not just a boundary in space and time, but also a boundary between different physical regimes, between the low-density, low-temperature, highly evolved conditions of the nearby universe and the high-density, high-temperature, primordial conditions of the early universe. And crossing that boundary means observing phenomena that do not occur in the present-day cosmos, processes that operated only in the first billion years, environments that no longer exist. And understanding those early conditions requires extrapolating our physical theories backward in time into regimes where they have not been tested, where the physics is uncertain, where quantum effects, relativistic effects, exotic processes might become important. The cosmic microwave background marks the edge of the observable universe in the temporal direction, the furthest back we can see using electromagnetic radiation. And beyond that edge lies the Dark Ages, the period before the first stars formed, when the universe was filled with neutral hydrogen gas, and before that lies the recombination era, when atoms formed, and before that, the era of nucleosynthesis, when protons and neutrons combined to form the first atomic nuclei, and before that, the quark-gluon plasma, the electroweak transition, the inflationary epoch, and ultimately, the Planck era, the first moments after the Big Bang, when quantum gravity becomes important and our current theories break down. And this is the point where our assumptions start to bend, because the further back in time we go, the less certain our understanding becomes, the more we rely on extrapolations and speculations, on theories that have not been tested experimentally, on physics that operates at energy scales far beyond what can be reproduced in laboratories. And the edge of the observable universe is also the edge of well-tested physics, the boundary beyond which we venture into realms where the laws of nature might behave differently, where space and time might not have the properties we assume, where the very concepts of distance and causality might break down. The Big Bang itself is not a moment we can observe, but an extrapolation, a singularity in the equations of general relativity that marks the limit of the theory's validity. And what happened at the Big Bang? What came before it? Whether the question of before even makes sense. These are questions that lie beyond the edge, not just of observation, but of current theoretical understanding. But this is where the universe begins to behave unexpectedly, because quantum mechanics and general relativity, the two pillars of modern physics, are incompatible at the Planck scale. The regime where quantum fluctuations of space-time become important, where the smooth geometry, assumed by general relativity, breaks down into a foaming, fluctuating quantum structure. And we do not have a complete theory of quantum gravity that describes how space-time behaves in this regime, how the universe emerged from the Planck era, what the initial conditions were, whether the Big Bang was truly the beginning or merely a transition from some earlier state. The edge of the observable universe points toward this deeper mystery, toward the question of origins, toward the fundamental nature of space and time and matter. And these questions remain open, unanswered, perhaps unanswerable with current methods. But they are the questions that drive cosmology, that motivate the search for deeper understanding, that keep the field alive with curiosity and wonder. Yet the deeper you look, the stranger the picture becomes, because even if we could observe the Planck era, even if we had a complete theory of quantum gravity, there would still be questions about why the laws of physics take the form they do, why the constants of nature have the values they have, why the universe is comprehensible at all, why mathematics describes reality with such extraordinary precision. And these are questions that physics alone cannot answer, questions that brush up against philosophy, against metaphysics, against the limits of human understanding. The edge of the observable universe is a reminder of these limits, a recognition that we are small, local, temporary beings, attempting to comprehend something vastly larger than ourselves, and the fact that we have learned as much as we have, that we can map the cosmos, trace its history, predict its future, is a testament to the power of observation, reason, and the scientific method. But it is also a reminder that there are boundaries we cannot cross, questions we cannot answer, mysteries that might remain forever beyond our reach. And in these mismatches, a different story begins to form, a recognition that the edge of the universe is not a single concept, but a collection of boundaries, each one marking a different limit, a different transition, a different kind of horizon. There is the edge of observation, the boundary beyond which light has not reached us. There is the edge of causality, the boundary beyond which events cannot influence us. There is the edge of measurement, the boundary beyond which signals are too faint to detect. There is the edge of understanding, the boundary beyond which our theories break down. There is the edge of knowability, the boundary beyond which questions cannot be answered even in principle. Each of these edges is located at a different place, defined by different physics, but they all point toward the same underlying truth, that the universe is larger than our capacity to observe it, stranger than our capacity to understand it, more mysterious than our capacity to explain it. But here is the detail scientists rarely discuss. This multiplicity of edges, this layering of boundaries, is not a failure or a limitation that diminishes the value of cosmology, but a feature that enriches it, that makes the quest to understand the universe more profound, more meaningful, more worthy of pursuit, because it reminds us that knowledge is not a destination but a journey, that understanding is not a final state but a process, and that the boundaries we encounter are not barriers but invitations to think more deeply, to observe more carefully, to question more rigorously. The edge of the universe challenges us to recognize our place within the cosmos, to acknowledge our limitations while also celebrating our achievements, to embrace the uncertainty while continuing to push against it. And in this tension between what we know and what we do not know, between the observed and the unobservable, between the measurable and the ineffable, lies the beauty of cosmology, the reason it captivates us, the source of its power to inspire wonder. Yet none of this fully explains what comes next. Because the story of the edge is also the story of perspective, of how observation depends on position, how reality appears different from different vantage points, how the universe we see is not the universe as it truly is, but the universe as it appears from here and now, filtered through layers of distance and time and the geometry of space-time. An observer in a galaxy 10 billion light-years away would see a different observable universe, overlapping with ours but not identical, revealing different galaxies, different structures, different regions of the cosmic web. And their edge would be different from our edge, located at a different place, encompassing different space, and yet both edges would be equally valid, equally real, equally shaped by the physics of light propagation and cosmic expansion. This multiplicity of perspectives is a fundamental feature of cosmology, a consequence of the relativity of observation, and it means that there is no single, objective edge that all observers would agree upon. No universal boundary that divides the cosmos into the observable and the unobservable. And this is the point where our assumptions start to bend. Because if the edge depends on the observer, if it varies from place to place and time to time, then many of the properties we measure, many of the parameters we infer, might also depend on our location, on our moment in cosmic history, on the particular region of the universe we happen to inhabit. And extrapolating those properties to the universe as a whole requires assuming that we are typical, that our region is representative, that the conditions here are the same as the conditions everywhere. And if that assumption is wrong, if we are atypical in some way, then our cosmological model might describe our local environment accurately, but fail to capture the true nature of the cosmos at large. This possibility introduces a fundamental uncertainty into cosmology, an irreducible ambiguity that cannot be eliminated by better observations or more sophisticated theories, because we are confined to a single location, a single perspective, a single moment, and we cannot step outside the universe to view it from an external vantage, cannot compare our observations with those of observers in distant galaxies to check whether we are seeing something typical or something unusual. But this is where the universe begins to behave unexpectedly, because there are hints, subtle suggestions in the data that our location might not be perfectly typical, that the local universe, the region within a few 100 million light-years, might have properties that differ slightly from the cosmic average. The motion of our galaxy relative to the cosmic microwave background, the so-called dipole, is larger than expected from the gravitational pull of nearby structures, suggesting that there might be large-scale flows, bulk motions of matter on scales of hundreds of millions of light-years, driven by massive concentrations of matter beyond our immediate neighborhood. The distribution of galaxies around us, the arrangement of clusters and voids, shows some asymmetries, some deviations from perfect uniformity. And while these could be statistical fluctuations, chance alignments in a fundamentally random distribution, they could also be signs of large-scale structure, features that extend beyond the observable universe and affect the region we can see. Yet the deeper you look, the stranger the picture becomes, because testing whether we live in an unusual region requires comparing our observations with the predictions of models that assume we are typical. And if the models are wrong, if they do not accurately describe the universe, then the comparison is meaningless, and we cannot tell whether the deviations we see are signs of atypical conditions or signs of incorrect models. This is a kind of circular reasoning, a bootstrapping problem that arises whenever we try to use observations to test assumptions that are themselves required to interpret those observations. And breaking the circle requires independent lines of evidence, alternative methods that do not depend on the same assumptions, ways of checking the models against reality that are robust to variations in our location or the properties of the local environment. And quietly, another contradiction appears in the data, because some of these independent checks give results that are not quite consistent with the standard model, that suggest tensions or discrepancies that might indicate problems with the assumptions, with the models, or with the observations themselves. And in these mismatches, a different story begins to form. A recognition that cosmology is a science built on inference, on extrapolation, on the assumption that the universe beyond our horizon is similar to the universe within it. And if that assumption is violated, if the cosmos is more varied, more inhomogeneous, more structured at the largest scales than we realize, then our picture of the universe, our understanding of its age, its composition, its geometry, its fate, might be incomplete or incorrect in subtle but important ways. The edge of the observable universe marks the boundary of what we can test, what we can verify, what we can measure directly, and beyond that boundary lies a realm of speculation, of models that are elegant and mathematically consistent, but that might not correspond to reality, that might be artifacts of our limited perspective, our partial view, our single snapshot of a cosmos that is far larger and far stranger than we can ever fully comprehend. Yet none of this fully explains what comes next, because the question of what lies beyond the edge is not just a question about space, about whether there are more galaxies, more structures, more regions of the cosmic web, but also a question about the nature of space itself, about whether space is infinite or finite, whether it wraps around on itself like the surface of a sphere or extends forever in all directions like an infinite plane. And these questions about topology, about the global shape and connectivity of the universe, are among the deepest and most difficult in cosmology, because they cannot be answered by local observations, by measurements made within a limited region, but require observations that probe the universe at the largest scales, at distances comparable to or larger than the observable horizon. And such observations are extraordinarily difficult, perhaps impossible, because they require detecting signals that are faint, subtle, easily confused with noise or foreground contamination. And this is the point where our assumptions start to bend. Because if the universe is finite, if space closes back on itself at scales larger than the observable universe, then light could, in principle, travel all the way around the cosmos and return to its starting point. And we might see multiple images of the same galaxies, the same structures, viewed from different angles at different times. And detecting these multiple images, these ghost copies, would provide direct evidence for finite topology, for a closed universe. But the observations required to detect such images are at the very edge of feasibility, requiring precise measurements of galaxy positions and properties across the entire sky. Statistical analysis that can distinguish true correlations from chance alignments, and the results, so far, are inconclusive. Consistent with an infinite universe, but also consistent with finite topologies that are larger than the observable horizon. And the question remains open, unanswered, one of the many mysteries that lie at the edge of what we can know. But here is the detail scientists rarely discuss. Even if the universe is infinite, even if space extends forever without boundary, there is still an edge to our observable universe, still a horizon beyond which we cannot see. And this horizon divides infinity into two parts: the part we can observe and the part we cannot. And the part we can observe is finite, bounded, limited by the age of the universe and the speed of light, while the part we cannot observe is infinite, unbounded, extending forever in all directions. And this creates a strange asymmetry, where the observable universe is a finite bubble embedded in an infinite cosmos, and everything we know, everything we can measure, everything we can say about the universe with certainty is based on this tiny finite sample, this infinitesimal fraction of the total reality. The edge of the observable universe in this picture is not the edge of space, but the edge of information, the boundary beyond which the universe exists, but cannot be observed, cannot be tested, cannot be known through any empirical method. Yet the deeper you look, the stranger the picture becomes, because this division of infinity, this partitioning of the cosmos into the observable and the unobservable, is not unique, not the same for all observers, and every observer in an infinite universe would see their own finite bubble, their own observable universe, and beyond their horizon would lie more space, more galaxies, more structure, all of it real, all of it existing, but forever inaccessible, forever beyond the reach of observation. And the totality of the cosmos would be the union of all these overlapping bubbles, each one finite, each one centered on a different observer, but the union infinite, unbounded, containing everything that exists, and no single observer could ever see the whole, could ever grasp the totality, could ever make measurements or perform observations that capture the full extent of reality. The edge of the universe is personal, individual, unique to each observer, and this personal nature of the boundary is one of the most profound implications of modern cosmology, a recognition that observation is perspective, that reality depends on who is observing and from where, and that the cosmos we see is not the cosmos that exists, but merely one view, one projection, one slice through a much larger whole. And quietly, another contradiction appears in the data, because this perspective dependence of the edge introduces ambiguities into the interpretation of cosmological observations, uncertainties about whether the properties we measure are local or global, whether they reflect conditions everywhere or merely conditions here. And these ambiguities cannot be fully resolved without observations from other vantage points, without data from observers in distant galaxies. And since we cannot communicate with those observers, cannot compare our measurements with theirs, cannot check whether we are seeing something typical or something unusual, we are left with uncertainty, with assumptions, with models that might be correct, but might also be systematically biased in ways we cannot detect. The edge of the universe, in this sense, is not just a boundary of observation, but a boundary of verification, a limit on what can be tested, what can be confirmed, what can be known with confidence. Yet none of this fully explains what comes next, because the philosophical implications of the edge, of this boundary between the knowable and the unknowable, extend beyond science, beyond empiricism, into questions about the nature of reality, the meaning of existence, the relationship between mind and cosmos. If there are regions of the universe that are forever beyond our observational reach, regions that exist but cannot be seen, cannot be measured, cannot be tested through any experiment, then in what sense can we say those regions are real? In what sense does their existence matter? And how should we think about a cosmos that extends far beyond the limits of human knowledge? These are not scientific questions in the narrow sense, not questions that can be answered through observation or experiment, but they are questions that arise naturally from the structure of space-time, from the physics of cosmic expansion, from the mathematics of general relativity. And they remind us that cosmology sits at the intersection of science and philosophy, of empiricism and metaphysics, of measurement and meaning. And this is the point where our assumptions start to bend, because the edge of the universe forces us to confront the limits of science, to recognize that there are questions science cannot answer. Regions reality cannot be accessed through empirical methods, aspects of the cosmos that lie forever beyond the reach of observation. And this recognition does not diminish the value of science, but clarifies its scope, defines its boundaries, acknowledges its limitations while also celebrating its achievements. Science is a way of knowing, a method for building reliable knowledge about the natural world, but it is not the only way of knowing, not the only source of insight or understanding. And the edge of the observable universe marks the place where science must give way to other forms of inquiry, to philosophy, to imagination, to speculation, to the recognition that reality is larger than what can be measured, stranger than what can be observed, more mysterious than what can be explained. But this is where the universe begins to behave unexpectedly, because the edge, for all its philosophical weight, is not an abstract concept, but a concrete feature of space-time, a boundary that can be calculated, mapped, studied through observations of distant galaxies in the cosmic microwave background. And this concrete nature of the edge means that it is not just a subject for philosophical speculation, but also a target for scientific investigation. A phenomenon that reveals something deep about the structure of reality, about the way space and time are woven together, about the relationship between observation and existence. The edge of the universe is where cosmology becomes most profound, where the questions become most fundamental, where the answers become most elusive. And it is this combination of concreteness and mystery, of measurability and inaccessibility, that makes the edge so compelling, so fascinating, so central to our understanding of the cosmos. Yet the deeper you look, the stranger the picture becomes, because the edge is not static, not fixed in place, but dynamic, evolving, changing as the universe ages and the expansion continues. And the future of the edge depends critically on the nature of dark energy, on whether it remains constant or evolves, on whether the acceleration continues indefinitely or eventually reverses. And these questions are among the most important in modern cosmology, because they determine not just the fate of the edge, but the fate of the universe itself. Whether it will expand forever, growing colder and emptier and darker, or whether it will eventually stop expanding and begin to contract, collapsing back toward a big crunch, or whether something else entirely will happen, some transition or phase change or unexpected phenomenon that our current theories do not predict. The edge of the universe, in this sense, is not just a boundary in space, but a boundary in time, a division between past and future, between the cosmos we observe and the cosmos that will exist billions of years from now. And in these mismatches, a different story begins to form. A story not of certainty, but of possibility. Not of answers, but of questions. Not of conclusions, but of invitations to explore further, to observe more carefully, to think more deeply. The edge of the universe is not a wall that stops us, but a horizon that beckons us. Not an ending, but a beginning. Not a limit, but an opening into deeper mysteries, stranger truths, more profound wonders. It reminds us that the cosmos is larger than our minds, that reality extends beyond our capacity to observe it, that there are aspects of existence we will never fully understand. And this reminder, far from being discouraging, is liberating, because it means there is always more to discover, always new questions to ask, always further to explore. And the journey of understanding is endless, rewarding, not because it reaches a final destination, but because each step reveals something new, something unexpected, something that deepens our appreciation of the strange, vast, beautiful universe we inhabit. There comes a moment in every long look at the cosmos when the mind tries to settle into certainty and then immediately slips again, as if the universe gently reminds us that its structure is not built for human intuition. The galaxies drifting outward are not simply moving through space. They are being carried by the very expansion that stretches space-time itself. And as this expansion continues, the edge we think we understand reshapes itself in ways that feel subtle from one moment to the next, yet monumental across cosmic time. Regions that were once inside our reach begin to fade. Others, long distant, slide outward until their light becomes too faint to trace. And the horizon, this strange, shifting threshold between what is knowable and what will forever remain hidden, rearranges itself slowly, silently, almost imperceptibly, like a tide that never stops flowing. But the deeper truth reveals itself only when we consider how every piece of ancient light behaves. The cosmic microwave background, that faint afterglow of the early universe, continues to cool as the expansion stretches its photons into longer and longer wavelengths. These signals we observe today as microwaves will one day drift into radio waves, then into wavelengths so long that no instrument can detect them. They carry with them the memory of the first moments after the Big Bang, the imprint of density variations, temperature fluctuations, the seeds of every galaxy that would one day form. And yet, even this oldest light is not permanent. As the universe ages, this glow will fade toward invisibility, sliding beyond the limits of any conceivable observation. What we now treat as our deepest window into the past will one day close, not with an abrupt boundary, but with a gradual dimming that makes the early universe itself disappear from view. And this leads to a quiet, unsettling consequence. As dark energy continues its work, accelerating the expansion, pushing distant galaxies beyond the cosmic horizon, the observable universe contracts in the only sense that matters. Fewer galaxies remain accessible. Fewer clues survive. The sky grows emptier. The patterns we use to reconstruct cosmic history become incomplete. And future observers, living billions of years from now, may inherit a cosmos in which almost all evidence of the Big Bang has vanished. Not because it never happened, but because the expansion has carried every trace beyond reach. Imagine a night sky with only a handful of nearby stars. Imagine a universe where no galaxy beyond the local group is visible, where no cosmic microwave background remains to be studied, where the clues that allowed us to understand the origin of everything have dissolved into unmeasurable wavelengths. Those future astronomers may look outward and see only darkness, and from that darkness, they may draw conclusions that contradict everything we know today, simply because the evidence will no longer exist. And here, the strange truth emerges with clarity. The edge of the universe is not a location. It is a relationship between light and time, between expansion and perspective, between what the universe once was and what it appears to be from where we stand. Our edge is unique to us, to our moment, our position, our tools. A civilization in a distant galaxy would see a different edge. A civilization living 5 billion years from now would see a smaller, dimmer universe. And a civilization living 5 billion years ago would have seen a cosmos far brighter, richer, and more compact. This relativity of perspective is not a flaw in our understanding. It is the nature of space-time itself. The universe does not grant a single, universal vantage point. It grants only local truths, each valid within its own horizon, and each different from the next. And perhaps the deepest mystery is this: the universe is structured in such a way that complete knowledge is fundamentally impossible. There will always be regions beyond reach, epochs beyond evidence, distances beyond measurement. The boundary between the knowable and the unknowable is not a failure of science. It is a feature of reality. And yet, within that limitation lies something unexpectedly beautiful. We stand in a moment of cosmic history, uniquely suited for discovery. We are early enough that the ancient light is still visible, yet late enough that galaxies have fully formed. We inhabit a universe that reveals just enough of itself for us to learn, to question, to imagine what lies beyond our horizon. And although that edge recedes, although the clues will fade, the act of looking outward, the slow, patient process of gathering light and making meaning from it, becomes its own form of connection. A reminder that the cosmos does not need to be fully known to be deeply understood. That understanding itself is an evolving edge, forever expanding just ahead of us, carried by curiosity instead of light.